All right, so hello and welcome everyone to week 12 of interactive live sessions for the course on fundamentals of convective heat transfer being offered by NPTEL and instructed by Professor Amaresh Dalal of IIT Guwahati. My name is Debjit. I'm a TA of this course and like every other week, we shall be solving some tutorial problems together. And as we know that this is the last session for this course, so here we go.
Sir, I think you have not started the recording.
Yes, I have. You don't need to worry about it.
Okay.
Okay. Okay. So this brings us to question number one of today's session, which says that in the pool boiling curve, the boiling curve for case of pool boiling, the point after the onset of nucleate boiling, where the heat transfer rate is minimum, is known as what? Is it option A, the inflection point? Is it option B, the Leidenfrost point? Is it option C, the critical point? Or is it option D, none of the above?
Leidenfrost.
Leiden frost point.
Okay, so very quick responses and in favor of option B, Leidenfrost effect. So if we look at the solution, indeed the Leidenfrost point is the, sorry, not Leidenfrost effect, I misspoke, the Leidenfrost point. So what happens is if we look at the pool boiling curve for water and atmospheric pressure, it goes something like this. It reaches a maximum, which is the critical point, then it goes down to the Leidenfrost point, and then it again goes on increasing. So this is the critical point. This is the Leidenfrost point, and here we are plotting the heat transfer rate versus excess temperature delta T, which is the T wall minus T saturation. And in the initial point, in this region, there is only natural convection. So what happens is if I take this, pool of liquid and then heat it from the bottom, I keep this plate at some T wall, at some temperature T wall. So what happens is when this excess temperature is low, there is only some natural convection currents being formed, and the evaporation takes place from the surface only. So this is the first regime, and then this is the first regime, and in the second regime, this point, this is called the ONB, or the onset of nucleate boiling, which I have mentioned over here in this question. So the onset of nucleate boiling means the bubbles start forming, but after forming also there is one region within which, so this is the case 2. Here if I again increase this wall temperature T wall a bit more, so here bubbles do start forming, but as they are rising, remember the rest of the liquid is at some lower temperature T saturation from the T wall. So as these bubbles go up, they get two things happen. One is they condense, they lose out the water, and they lose out material, and at the same time they get compressed. So compression and condensation both take place, and they finally cannot reach the surface. So this is you know one state, and then in the next state, so I'll draw these both states over here. There the bubbles do get smaller, or they coalesce with others. Some many interactions happen, but finally they are able to reach the surface, and they are those bubbles burst and they are released as vapor. And this goes on until a critical point where the bottom surface, this gets filled with more and more blobs of such vapors, and at a critical point, and after this, the transition begins where these blobs, they go on increasing. So this is for case 4. So these blobs, they go on increasing, and at the at this critical juncture called the Leidenfrost point, the entire bottom surface, it is filled with vapor blanket. So this I'm calling a vapor blanket. So the entire liquid in contact with the hot surface, it gets vaporized, and it forms a sort of division between the remaining liquid and the uh, bottom surface or the heating surface. And as a result, the heat transfer rate as a result decreases because this is providing a resistance. And this minimum point is called the Leidenfrost point. Now, if we go on increasing this excess temperature, some additional effects come in, which is the radiation from this surface into the liquid. This goes on increasing, and as a result, the Q again starts increasing. So all these multiple effects, they result in this very interesting feature of this curve, which has one maxima, one minima, and then again goes on increasing. Okay, so another, do you know about, does anyone know about Leidenfrost effect, which I mistakenly talked about earlier? Like I misspoke while trying to say Leidenfrost point, I talked about Leidenfrost effect. Does anyone know what is it?
No, sir. No, sir.
So So what happens is if I, take a, this is very much visible in Indian kitchens. So if we are trying to fry something, let's say if we're trying to fry a dosa, so what the chef would usually do is they would, take a little bit of water and then splatter it on the pan. And what would happen is if the pan is sufficiently hot enough, it won't, those, droplets of water,
It was.
they won't evaporate away immediately. It would stay for a while and dance around the pan. So this occurs as a result of Leidenfrost effect. So if we take a closer look at it, so let's say this is the hot surface, and we put one drop of water over it. So what happens? So the thing that we see in Leidenfrost point, that a vapor blanket forms. So similar things happen. So in this part of the bottom part of the droplet, that bubbles, and there is a vapor blanket forming just beneath the droplet, in between the droplet and the hot surface. Any questions? Okay. Anyway, so this vapor blanket forms, and as a result, this droplet does not immediately, vaporize, and it keeps on dancing on the pan for a certain period of time. This similar effect has been studied more formally by Leidenfrost, and as a result, the name has been given after him. Uh, but there are some, very old records which talks about the recipe of frying a dosa, and in that recipe it's actually written that the pan must be hot enough. When some droplets are sprinkled on it, they should dance around and not immediately boil off. So you know it's some lost history along with lost science. Okay, any questions regarding all of this?
Sir, I have a question. In stage number three,
Yeah.
the instructor said that the rate of heat transfer coefficient slightly decreases.
Yeah.
So, what is the reason?
Yeah,
of
so here these, the area in contact between the liquid and the hot surface, that decreases after a point, which is known as the inflection point. So before this, H would be increasing, and after this point, H would be decreasing, and that happens due to that fact that the area in contact between the liquid and the hot surface, that gets decreased due to this, bubbles forming and taking up a lot of the area. Makes
Okay,
sense?
sir. Okay.
So let's say if we take two different situations. So at a lower temperature, let's say there is this only one single bubble forming, and this much area is available. So what happens later on, that there are two bubbles forming, and those bubbles, I'm saying they're vapor bubbles. So, and they are getting bigger in size as well, and as a result, the resultant area of heat transfer, the area of contact between the liquid and the hot surface, that decreases. That's the reason why H decreases. Does that make things clear?
Okay, sir.
Okay. So if there are no more questions, we will move on. We'll move on to question number 2. So arrange the following stages of flow boiling in subsequent order. So what is flow boiling? So if I have a hot tube and I'm passing some liquid in it, and this entire tube is supplying some heat to it, and this liquid is eventually getting converted into vapor. So but there are some very distinct stages of this happening. Uh, so there are six options given here. You'll have to arrange them in the subsequent order, starting from the first stage to the last stage. So the six stages are slug flow, option B mist flow, C annular flow, option D bubbly flow, option E single phase liquid flow, and option F single phase vapor flow.
So it is E D A E
Let
D
me write
F.
one second. One second. Please repeat. E.
E D for Delhi,
Hmm.
A E B
B for
B for
Bombay.
Bombay,
B for Bombay.
and F.
F. Okay. Any other answer? Sorry, I've written E twice here. Am I right, or did you mean something else?
It is C, sir. C.
Okay.
The second E is to be replaced by C. I
This would
told
be
you
C,
wrong.
right? Okay.
C.
Okay. Good. Any other answer?
No, this is correct, sir.
This is correct, you think? Okay. So we'll have a look at the correct order, and it is indeed E, D, A, C, B, F. So if we go back to our flow boiling case. So initially when the liquid enters, it is in a liquid stage. So this is single phase liquid flow. So this would be E. Then in the second stage, some bubbles start appearing. They start forming. They form near the wall and then move inside due to fluid motion. And this region is called the bubbly flow, which is option D. In the next stage, these bubbles, they get bigger and they even coalesce with each other to form even bigger bubbles. So it's basically these big bubbles filled with some spaces of liquid, and this kind of a flow is called a slug flow. So this is option A, slug flow. And now once it has entirely filled up a great region in between, the majority of the region within. So there would be liquid only along the walls, and there would be vapor in between. And this region is called an annular flow because it's forming an annulus concentric to the pipe along which it is flowing. And when there is no more liquid remaining, the entire liquid has been vaporized and it forms a homogeneous mixture, then that's called a mist flow. And when it has entirely shifted from the mist into the vapor phase, that is known as the single phase vapor flow. So in the mist flow also, there are it's at a mixture stage. There is vapor mixed with some very small liquid droplets being homogeneously spread around. And in vapor flow, it's entirely vapor. There is no more trace of liquid remaining. So this is the correct order: E, D, A, C, B, F. Okay. Okay.
Okay.
So if there are no doubts, we will move on to third question of today's session. So this is again, some arrangement has to be done. So arrange the following stages of pool boiling in order of increasing excess temperature. So this is something that we recently discussed. So I think it will be very easy to answer. So options are option A film boiling, option B natural convection boiling, option C nucleate boiling with bubbles reaching the surface, option D nucleate boiling with bubbles collapsing, and option E transitional boiling.
B for ball.
B, huh?
BDCEA.
Right,
C.
BD.
D. D
D.
for dog.
Okay, so any one of you answer. I'm getting confused.
B for ball.
B for ball,
D for dog.
D for dog,
C for cat.
C for cat,
E for eagle.
for eagle, and then
A for apple.
A for apple. So B, D, C, E, A. Let's have a look at the correct answer. And it is indeed B, D, C, E, A. Is this one the one? Yeah, B, D, C, E, A. So B, natural convection boiling, which we saw was the first stage. Then, after onset of nucleate boiling, there are two subsequent stages. One where this collapses. So this is the first one. So and this would be the second one where the bubbles collapse, and then the bubbles somehow manage to survive and reach the surface. This is stage three. Then there will be transitional boiling when the heat transfer rate actually decreases, and then film boiling where it ultimately reaches its minimum. So this is the correct order: B, D, C, E, A. Okay. I hope there are no questions regarding this one. We will move on. Move on to question number 4 now. This is a numerical type question. So what we have here is saturated steam at saturated temperature of Tsat equal to 100 degrees Celsius condenses on a plate which is tilted at 60 degree from the vertical and maintained at 90 degrees Celsius by circulating water through the other side. That doesn't matter, but anyway, it's being maintained at 90 degrees Celsius. Now, the rate of condensation of steam is what? Now, we'll have to assume wavy laminar flow, use the relation which is given here, this relation, and the data given are Reynolds number is 920.5. The conductive heat transfer coefficient of the liquid is 0.677 watt per meter Kelvin. The latent heat capacity HFG, that is 2286 into 10 to the power 3 joules per kg, and the kinematic viscosity nu L for liquid is 0.309 times 10 to the power minus 6 meters per second. So have a shot at it, then we will try to do this together. take your time, no need to rush. Just do this entire thing correctly. And if you have any questions or you want to discuss the method or anything, feel free to ask.
Yes, sir.
So let's discuss about the primary method of trying to approach this. As we know, for any kind of heat transfer process, we know that the rate of heat transfer, this is equal to whatever phase change rate is going on in the latent heat. So here, this HFG, this latent heat capacity is known, and this has to be found out, the condensation rate. So in order to find this out, this heat transfer rate also we need to know.
Sir, answer is 4.91 into 10 raised to minus 4.
4.91
91 into 10 raised to minus 4 kg per second.
minus 4 kg per second. Okay, we will look into it. So this is one answer that we are giving. We will see if we land in the correct answer. So uh, back to the method. So if we now look at this, so we need to find out the heat transfer rate between the surface and the the material which is condensing or boiling. And for this, in order to find out this, we need H, and we will simply use Newton's law of cooling. So HA into delta T. HA into delta T. So delta T we know, area we know, we can calculate from the dimensions. H has to be found out using this relationship. So the relationship of H we know, this is given. From here we will find out Q, and then after plugging Q into this equation we will finally find out this m dot. So let's get into it. So first of all, we know this expression of H. This is given as RE case of XL divided by 1.22, sorry, 1.08 into RE to the power 1.22 minus 5.2, and this is into G cos theta since it is slant at an angle. So instead of G, we will use G cos theta. So this would be G cos theta divided by mu L to the power 1/3. Now plugging in all the values, RE we know as 920.5 into KL we know to be 0.677. Now divided by 1.08 multiplied by 920.5 to the power 1.22 minus 5.2, and here we have 9.81 into cos 60 degrees divided by nu L. So nu L is 0.309 into 10 power minus 6. 0.309 into 10 power minus 6. And this whole thing to the power 1/3. Okay, so I will get my calculator. Okay, so 920.5 to the power 1.22 this multiplied with 1.08.
Sir, what is the value of HFZ? Can you
What?
HFZ, latent
This
heat?
is the value. Okay, value is 286 into 10 to the power square.
Okay, okay.
So that is G cos theta upon mu L square. You have written mu L.
Sorry.
G cos theta. That is G cos theta upon mu L
Oh,
square.
square. Yeah, sorry, I missed the square. Thank you. I've got it wrong. So this one, 4456.85 into 0.677. And this one, if I try to calculate now, so cos 60 is half into 9.81 divided by 0.309 into 10 power minus 6 square. So this is 5.13 to the power into 10 to the power 13. Now this has to be taken cube root of. So take cube root of that. This goes down 37, sorry, 37174.19. So this multiplied by 920.5 into 0.677 divided by 4456.83. Okay, so this gives us a H of around 5197.89. So we can see that since it is a phase change heat transfer process, the H is in the range of above 5000, pretty high. Okay, so we have found out H. Now the next step was, if we go back, so the next step was to use this H to find out the heat transfer rate. So now the heat transfer rate I will find out as HA into delta T. Now H we found out to be of this value. The area is 8 meters into 3 meters. It's 24 meters square. And temperature difference is this, this inclined plate was being maintained at 90 degrees Celsius, and the steam outside was at its saturation temperature of 100 degrees Celsius. So this temperature difference I'm writing down directly as 10. So if we do this, so 240 multiplied by this value, 5197.89. So this is something of this sort, 1.7 into 10 to the power 6 watts. And for the next step, we'll equate this with the rate of latent heat being transferred. So instead, we can write down this as Q dot equal to M dot into HFG. And now we will calculate M dot as this heat transfer rate divided by the latent heat capacity. So this was found out to be 247 into 10 to the power 6, and HFG we know is 2.2286 into 10 to the power 6 in kg per second. So 10 to the power 6, 10 to the power 6 goes away, and 1.247 divided by 2.286. I reckon it is something around 0.5. So yeah, M dot is around 0.545 kgs per second.
My answer is, sir, 0.4911.
0.4911.
Because see that bracket na 33460. Can you go next slide? This one. It is 37174 na after bracket.
Yeah.
This is my answer coming 33,460.
See, this is very straightforward. I can recheck it if you want. So it's nothing but 9.81 into cos 60. Cos 60 is 0.5. So I'll do this.
So 9.81 into 0.5. It is.
Yeah, and divided by 0.309 into 10 to the power minus 6 squared. So this comes out to be 5.137 into 10 to the power minus 13 before taking the cube root. So this
10 raised to power 13, na?
Yeah.
Positive 13.
Yeah.
Yes.
This is up to this is correct?
5.137 into 10 raised to 13.
Okay, so if I now take cube root of that value, it comes out to be this only 37174. Can you check? Are you how are you doing the cube root? Are you taking 0.3 as the power?
Yes.
So that could be the reason. Take 0.33333, or there is a cube root.
Yes. I am taking 0.33 value, na?
Yeah.
So that's why the difference is coming.
Due to that approximation, it's a big difference. Anyway, so your answer was what? 0.419.
0.49.
The order of magnitude is the same, if not the exact value is the same. Okay.
Okay.
All right. So this is how we can do this. There were multiple steps in it. We broke them down simply and then approached each one at a time. So any questions regarding this?
No.
No. If there are no questions, we will move on. We will move on to question 5 of today's session. So the convective coefficients for condensation usually lie in the range option A 30 to
Option D.
300, option B 50 to 2000 watt per meter square Kelvin, option C 200 to 10,000, and option D 5,000 to 1 lakh watt per meter square Kelvin.
5,000 to 1 lakh. D.
So option D is the answer for both of you.
Yes.
And that is indeed correct. So That is a primary reasons why phase change heat transfer is so much sought after, while trying to engineering very some systems where heat has to be removed or added very quickly. So the value of H, which has a great influence on how fast the rate of heat transfer is. This is very high in cases of phase change heat transfer. So all the cutting edge technology, which has to employ a very high heat transfer rate, there this phase change heat transfer methods are used in one way or the other. Okay, but it comes with plenty of challenges. So first of all, we saw how difficult it is to model the methods themselves. On top of that, the it's never usually pool boiling or pool condensation kind of thing. There are usually flows within it, and due to this phase change, we see that most of them will have multi-phase flows, and multi-phase flows are a different challenge. They bring their own set of difficulties along with them. So that's why this entire thing is very effective, but very challenging as well. So it requires more study, and in future many more advancements we can expect to come out of this field. Okay, so moving on, we'll move on to question 6. This is a simple one. So drop wise condensation usually occurs on what? Option A, oily surface; option B, glazed surface; option C, smooth surface; or option D, coated surface.
Coated.
Okay,
Coated surface.
coated surface. So if we look at the correct solution, indeed coated surface. So condensation, how many types are there? What did we study?
Drop wise and film wise.
So there are two types, drop wise and film wise. So if we look at the two cases, so in the drop-wise case, small droplets form, and some of them, coalesce with each other to form a bigger droplet, and those bigger droplets they, trickle down due to gravity and picking up other droplets with it along the way. Uh, so this is how drop-wise condensation occurs, and in film-wise condensation, the there are no individual droplets, but instead a layer of liquid gets condensed from the vapor phase, and it forms a boundary layer sort of a thing. Not a boundary layer per se, but the kind is similar, and we saw the math of it as well. So they do resemble each other. There is this film thickness delta, which is analogous to the boundary layer thickness delta as well. But of course, those are very separate things. Let me give this warning sort of. They are similar but not the same. So drop-wise condensation. This is usually seen in coated surfaces where there is some silicon, Teflon, or other kind of polymer coating is given. Uh, So in coated surfaces, drop-wise condensation is more, prevalently seen. Okay, let me ask another question from this. So between drop-wise and film-wise, which one has a higher value of heat transfer coefficient?
Drop wise.
Drop-wise. Why?
Because the
Because
surface
there is
is
no
exposed to the
resistance
vapor.
wall for heat
Surface is
transfer.
exposed to the vapor.
No resistance is not the correct answer. Yes. What is
Surface
the
is
other answer then?
surface is exposed to the vapor.
Correct.
Most of the surface is exposed to the vapor
Yeah,
directly.
so if we look at these figures, so in this figure we can see that the film has covered the entire surface, and between the vapor and the solid surface, which is cooling it, or the cooling surface, the contact is very less. So let's say there is one packet of steam over here, so all it interacts with is with the liquid. So this condenses and gets added to the liquid. But here in case of drop wise, the packets of steam, they come directly in contact with the surface, and they can lose the heat much more easily and then form droplets. So that's why in case of dropwise condensation, the H is more. So if we recall, there was a curve like this, where this was for dropwise, and let me take a different ink color, and this one was for the film. This was temperature difference, I guess, and this was the convective heat transfer coefficient. Do you recall this curve?
Yes, sir.
Yeah. So any questions regarding all this?
So I have a question. In film-wise condensation, you have drawn the diagram there.
Yeah.
So I'm asking the question. The Reynolds number, while calculating the Reynolds number, we need to calculate the hydraulic diameter. So
Yeah.
while calculating that,
Hmm.
that perimeter was taken as the width of the plate. So I
Yeah.
didn't understand that why perimeter is taken as only width.
Yeah. See, in while calculating Reynolds number for any case, there has to be a characteristic length. Now, in this case, the length would actually go on. So if I take this, x direction, we don't, stop at any L. This could go on forever, right? So this dimension is not bounded. That is why, the width multiplied with, some unit length, 1. So width into this unit length 1, this is taken to be as the perimeter. Makes
But
sense?
but the perimeter is actually the summation of all the sides of the area.
Yeah, true. But
So still it is definite.
mm, the along this x direction, there is this variation of the film thickness, and uh, all the everything that is happening, it's happening in the x direction, and there is no any characteristic length L corresponding to other cases that we can think about to be considered here. So that's why along the width there is no variation, and a unit dimension is taken in the lengthwise direction or the span-wise direction, then that is taken as the perimeter. And apart from this, there is another definition of Reynolds number as well, where the characteristic length was taken to be something else altogether. Do you remember that?
Yes, sir.
So it was something like mu square by g to the power something. Let me do this. So it is meter square per second. Sorry, meter to the power 4 second square, and this is meter per second square. Yeah, so yeah, this was to the power 1/3. So here the length scale, which is Reynolds number, what we know, the usual thing is UL by nu, right? So
Yes.
since there is no characteristic length scale associated with the problem, we will find another length scale which comes from the properties. So here nu is what? It is property of the fluid, and g is the acceleration due to gravity. But if we manipulate this mathematically, nu square by g to the power 1/3, this gives the dimensions of length. Okay,
Hmm.
so we can incorporate this as well in order to find out the Reynolds number.
Okay.
Okay, so this is the issue. Like in some cases, there is a characteristic length very prominently. We can see that this should be the length scale. Like if it's a sphere, it could be its diameter. If it's a pipe, it could be its diameter as well as length as well, depending upon the application.
Hmm.
But in less general cases, some specific cases, or there's cases with some infinite dimension in one direction, there in the absence of a prominent length scale, we try to find out something else.
Okay.
Right. Moving on, we move on to question number 7 of today's session. So from muscle analysis of laminar film condensation, the film thickness delta varies as x to the power n. Now this n is equal to what? Is it option A 1 by 4? Is it option B minus 1 by 4? Is it option C 1 by 3? Or is it option D 3 by 4?
1. I don't remember it.
1 by 4.
Our answer is 1 by 4.
No, not exactly.
Is your answer?
Can't recall.
Okay. So if we look at the correct solution, 1 by 4 is the correct answer. So delta was proportional to x to the power 1 by 4. It came directly from laminar film condensation analysis. If we try to recall some of the earlier steps which led to this, to remember there was this one delta into d delta q by delta x equal to something. So by integrating this, we got delta raised to the power 4 something into x. And then if we try to find out delta, it would be that something to the power 1 by 4 and x to the power 1 by 4 as well. Remember this? This was one of the previous steps within the derivation. Anyway, so you can go back and have a look at the derivation. This is how it goes, and n is this is actually important because if we try to find out that there is this vertical plate of say length L that we know, now to estimate what would be the maximum film thickness. So from this we can get that from this relation. It relates delta to the x. Okay.
Okay.
So this was the last question of today's session, and this last session of the entire course as well. So it has been a great learning experience from my end. I hope I could make a good learning experience from your side as well. So thanks a lot, and we'll meet again some other course in the future.
Yes, sir. It
Yes,
was
definitely.
very good learning experience from our side also. So whatever doubts we had while listening the session, those were cleared in the online sessions. So thank you from our side also. Thank you very much, sir.
Thanks a lot.
Okay. Thank you, Debjit sir.